All right, let's talk about the hidden energy that's literally everywhere, powering everything from a campfire to the engine in your car. We're diving into thermochemistry, the science that explains what makes things hot or cold, and how we can measure all that energy being traded back and forth.
I mean, really think about it. You snap one of those instant cold packs, and it gets icy cold. How? It's literally sucking heat out of you. That's an endothermic process. And a bonfire? That's an exothermic process, throwing off massive amounts of heat. So where does that energy actually come from? And how can we put a number on it? Well, that's exactly what we're going to figure out.
So here's our game plan for today. We're going to start with the basics of what heat actually is. Then we'll get our hands on the tool we use to measure it, the heat equation. After that, we'll see how scientists trap and trade heat in the lab, uncover some hidden energy, and finally, wrap it all up with a concept called enthalpy and see how it applies to, well, pretty much everything. All right, first things first, we can't talk about measuring heat if we don't know what it is. So let's get a handle on this fundamental idea. So what is heat? The key thing to remember is that it's not a thing, it's a process. You can think of every molecule in an object as jiggling around. The more they jiggle, the more thermal energy they have, and the hotter the object feels. Heat, which we'll call Q, is just the name we give to that energy when it's on the move from one place to another. And this movement isn't random. It's a one-way street. Just like water always rolls downhill, heat always flows from something hot to something colder, never the other way around. And it keeps flowing until both things reach the exact same temperature. We call that state thermal equilibrium. It's when everything is balanced out and the net flow of energy stops. Okay, so if heat is this flow of energy, how can we measure it? How can we quantify it? Well, that brings us to our next part, the heat equation. Think of this as our ruler for energy. To use our ruler, we need to know about a property called specific heat capacity. We use a lowercase c for it. You can think of it as a substance's personality, or its energy fingerprint. It tells you how stubborn a substance is about changing its temperature. A low specific heat means it heats up and cools down really easily. A high specific heat means it can absorb a ton of energy without getting much hotter. And you've totally seen this in action. Picture a hot day at the beach. The sand is scorching, right? You can barely walk on it. But the ocean water is still pretty cool. Why? It's all about specific heat. The sand has a low specific heat, so the sun's energy makes its temperature skyrocket. Water, on the other hand, has a very high specific heat. It can soak up that same amount of energy, and its temperature barely budges. And this all leads us to the main event, our workhorse equation, Q equals mc delta T. Let's break that down. Q is the heat we're trying to find. M is just the mass of our substance. C is that specific heat capacity we just talked about, and delta T is just a fancy way of saying the change in temperature. Let's actually use it. Let's say we heat up 800 grams of water from a room temperature of 21 degrees Celsius to a piping hot 85 degrees. Okay, step one, what do we know? Our mass M is 800 grams. The specific heat C for water is always 4.184 joules per gram degree Celsius. That's just a number you look up. And our temperature change, delta T, is the final temp minus the initial temp, so 85 minus 21, which is 64 degrees. Now we just plug it all in and multiply. And boom, we get our answer. About 210,000 joules of heat were absorbed by that water. See? Not so bad. So doing the math on paper is one thing. But how do scientists actually measure this in the real world? Well, that's where calorimetry comes in. It's the science of trapping and trading heat. The first step in any calorimetry experiment is to draw a line in the sand. We define our system, that's the chemical reaction we're actually interested in. And then there's the surroundings. That's everything else that can exchange heat with our system, like the water it's in, the cup, the thermometer, you name it. Now here's the clever trick. It's really hard to measure the heat of the reaction directly, but it's really easy to measure the temperature change of the surroundings. So if our system is exothermic, it releases heat, which warms up the surroundings, and we see the thermometer go up. If it's endothermic, it absorbs heat from the surroundings, making them colder, and the thermometer goes down. We measure the surroundings to figure out what happened in the system. And the whole thing is built on one simple, beautiful, unbreakable rule. Energy can't be created or destroyed. In our sealed-off calorimeter, any heat that the system loses, the surroundings must have gained. And any heat the system gains, the surroundings must have lost. So the heat of the system plus the heat of the surroundings always adds up to zero. This is the heart of all calorimetry. Okay, so far we've been saying that adding heat changes the temperature. Simple enough. But what if I told you that sometimes you can add a ton of heat and the temperature doesn't change at all?
No, really, think about this. You've got a pot of water at a full rolling boil. A thermometer in there would read 100 degrees Celsius. Now, if you keep cranking up the heat on the stove, you're obviously pumping more energy in, but the thermometer will stay locked at 100 degrees. So, what gives? Where is all that extra energy going if it's not making the water hotter?
That energy has a totally different job to do. Instead of making the water molecules jiggle faster, it's being used to break the bonds holding them together as a liquid, allowing them to escape as a gas. We call this the enthalpy of vaporization. It's the hidden energy that's required for a phase change. Its mission isn't to raise the temperature, it's to change the entire state of matter. And you guessed it, we can calculate this too. Let's say we need to boil 100 grams of sulfur dioxide. We look up its enthalpy of vaporization, which is 25.1 kilojoules per mole. Okay, first we need to convert our 100 grams into moles using its molar mass, which gives us about 1.56 moles. Then it's just simple multiplication. 1.56 moles times 25.1 kilojoules per mole, and that gives us our answer. It takes about 39.2 kilojoules of pure energy just to turn that liquid into a gas, without the temperature changing one bit. Okay, let's pull all these ideas together now and introduce one of the most important terms in all of thermochemistry, enthalpy. Enthalpy, which we write as a capital H, is basically the total heat content of a system. Now, we can never really know the total heat content, but what we can measure is the change in enthalpy, or delta H. And here's the crucial link. For just about any reaction happening out in the real world at constant pressure, this change in enthalpy, delta H, is equal to the heat flow, Q, that we've been calculating all along. It's the professional term for the heat of a reaction. Using delta H gives us a really simple and clean way to talk about this. If a reaction releases heat, if it's exothermic, then its delta H is negative, because the system lost heat. If a reaction absorbs heat, if it's endothermic, its delta H is positive, because the system gained heat. So from now on, when you see a negative delta H, think gets hot. And when you see a positive delta H, think gets cold, just like that instant cold pack.
So why should you care about any of this? Because enthalpy is everywhere. It's how we measure the calories in your food. It explains how our bodies generate heat. It's absolutely critical for designing better fuels, more efficient air conditioners, and even the search for new renewable energy sources. Understanding enthalpy is understanding the language of energy itself. Which leaves us with a final question. We've started by just wondering why some things feel hot and others feel cold. Now we have the tools to precisely calculate the energy flowing through pretty much any process you can imagine. The big challenge now is, what do we do with that power? How can we use this deep understanding of energy to design and build a smarter, more efficient, and more sustainable world? That's the real test.